Welcome back. So we were discussing the chemical reaction, and in the last lecture we went through the definition of air-fuel ratio, and as well as discussed some examples of the types of fuel. Okay, we also discussed that the moles are not balanced. It's a conservation of mass balance, which we are going to make use in order to analyze the chemical reactions for combustion processes. Okay, so in this lecture I will continue that discussion and present some of the combustion analysis, particularly the percentage of theoretical air, and we will try to do some energy balance for reacting system for both steady flow control volume and fixed mass systems. Okay. As we realized in our basic analysis that there is a possibility of that some of the combustion can not lead to the completion due to for example, if the air is not sufficient, or there is a possibility that excess air is given, so the combustion is complete, but you still have some of the air left in the product stream. So a combustion process is complete only if the combustible components of the fuel are burned to completion. Okay, so this is kind of a theoretical estimate. Okay, and many times you may have to provide little more because you may not know exactly the contents of the fuels, or you would like that absolutely the fuel should be burned. So hence we need to add more fuel in order to add more oxidizer or air in order to have complete combustion. Okay, so there is a theoretical limit. So we call it theoretical air percentage. So let me just go through that. So this is an example of let us say fuel and air leading to CO2, H2O, O2 and N2. Okay. So this is a typical kind of product which will form when you burn hydrocarbon fuel. Okay. So as I said, air could be in excess, and hence you may have stream not just inert components such as the nitrogen, but excess oxygen also along with CO2 and H2O as a final product. Okay. Now oxygen has a much greater tendency to combine with hydrogen than it does with the carbon, and therefore usually you will see after the completion of the combustion you will be the product will contain mainly H2O plus CO2. So thus the hydrogen in the fuel normally burns to completion forming H2O. Okay. So this is more possibilities beside of course forming CO2. Let me just go through the definition of complete and incomplete combustion. So the complete combustion is if all the carbon in the fuel burns to CO2. Okay, so that means CO2 has to be present, and all the hydrogen burns to H2O, and all the sulfur, if any, burns to SO2. Okay. Now we are quite well aware that SO2 and CO2 are not so good for environment. Okay, but this is something which also relies that reduction in the carbon in the fuel and sulfur in the fuel is critical to have better fuel or the more environmentally friendly fuel. Okay. Now if there is an incomplete combustion, then the combustion product contains components such as C, H2, CO and OH. Okay. So what are the reasons for incomplete combustion? Of course the first is that you don't have sufficient air or sufficient oxidizer. That means insufficient oxygen. Okay. Another possibility would be that insufficient mixing may be present in the combustion chamber, which during the limited time fuel and oxygen are in contact. So if you don't allow fuel and oxygen to have a proper contact, that means the time is limited, and hence it doesn't mix well, and then it doesn't burn. So this is another possibility. The other possibility could be that the temperature could be very very high in the combustion chamber, leading to dissociation. Okay, and thus it will not go through the regular mechanism of reaction. Okay, so there is a certain theoretical limit for complete combustion. One can do a simple reaction balance here or elemental balance and try to get the theoretical estimate of the AF which is required for 100% combustion of the fuel. So this is what we define as theoretical air, or sometimes also called stoichiometric air, which is the minimum amount of air needed for the complete combustion of the fuel. Okay, so it's also referred to as the chemically correct amount of air or 100% theoretical air. So the stoichiometric or theoretical combustion is the ideal combustion process during which a fuel is burned completely with the theoretical air. So this is an example of combustion of methane. So methane takes like 1 mole of methane will take 2 moles of oxygen, leading to complete combustion of CO2, H2 water, and whatever remains, the inert will be will come out as it is. Okay, so this is the complete combustion with no free oxygen in the product. Okay, and thus this is also a theoretical combustion. So that means the theoretical air here is nothing but some 2 into 4.76 kilomole of air. So that is something which you would call theoretical air. This becomes a kind of a limit or kind of a criteria for which we can add additional amount of air in terms of access, okay, in order to have surety that the combustion will lead to completion. Okay, thus we define other terms such as excess air, which is the amount of air in excess of the stoichiometric amount, and usually this is referred in terms of percentage excess air or percentage theoretical air. Okay, so our deficiency of air, which is the amount of air less than the stoichiometric amount, often expressed as a percentage deficiency of air. Equivalence ratio, though is not very commonly used, is the ratio of the actual fuel air ratio to the stoichiometric fuel air ratio. Okay, so this is an example of a typical way of using this excess air or theoretical air. So if somebody says like 50% excess air, okay, it means nothing but the theoretical air plus 50% of the theoretical air, which means that this is nothing but 150% of the theoretical air. Okay, so this is nothing but your theoretical air plus 50% of, okay, which is nothing but 150% of theoretical air. So 200% of excess air is nothing but, of course, the same logic is a 300% theoretical air. 90% of theoretical air is 10% deficiency of air. Okay, so this is the different terminology which we are going to make use of it in our analysis. Okay, now how do you find or analyze the product of the combustion? Okay, so this is something which is important in order to see whether combustion is complete. Okay, and thus this is a kind of a critical part of your combustion reaction to analyze the gases which are formed in product. So predicting the composition of gas product is relatively easy, okay, when the combustion process is assumed to be complete. However, it is not possible to predict the composition of the product on the basis of mass balance alone with actual combustion process. So then the only alternative we have is to measure them amount. So what we are trying to say is that many times it's not feasible to assume that the combustion is complete, and thus it's critical that you analyze the product gas composition. And this particular analysis is typically done by something called Orsett gas analyzer, okay, which are reported on a dry basis bed. That means the water is not considered in the analysis of it. Okay, that's the meaning of the dry basis. Okay, so we will be assuming that the composition which we have been given is either through Orsett gas analyzer in general. Okay, so whether it's a dry basis or wet basis, that's something which will be provided to us. So this is an example. Okay, here an octane is burned with dry air, which essentially means doesn't contain any moisture, and this is the analyzer volumetric analysis of the product on a dry basis, of course using some kind of an analyzer such as your Orsett gas analyzer. And what we need to find is the air fuel ratio and the percentage of theoretical air used. Okay, and the other thing which we have to calculate is the percentage of theoretical air used. So let me start with the basic equation here. So of the combustion of octane, it's not being mentioned that the amount of octane which is being burned. Okay, what we know is the composition of the product first of all, but that also with a dry air. We should also assume that there is a water, because as we know the hydrogen will burn completely leading to water in the product. That means we need to write something like this, that you have octane, let's assume that you have X mole of octane, this is burned with certain mole of oxygen, that means oxygen plus nitrogen. So this is the A mole of it, leading to, this is volumetric analysis, so we are on a dry basis, so let's assume this as 10.02 CO2 plus 0.88 CO and some amount of water. Okay, so now we have this equation where a lot of unknowns are there, and the only way we can solve this problem is by doing a mass balance of each element. Okay, so let us assume that there is a, so what we have done in this case of course is we have assumed that 100 kilomoles of dry product is used. That's why we can clearly write this as the number of moles for product for the dry products. Okay, of course we don't know about the water, thus we written B moles of water being also as a part of the product. Okay, so we have this equation. Now what we can do is we can write mass balance for individual components. Okay, so let's write this is for nitrogen to start with. Okay, considering N2 rather than N, 3.76 is on the left side multiplied by A. This should be equal to 83.48, leading to A is 22.20. Okay, what about carbon? 8x is 10.02, which is from here, plus 0.88 for carbon monoxide, leading to X is 1.36. Then you have 18.6 is equal to 2, 18x equals to B, B is 12.24. Okay, now at this point you have all the values of AXB. You can also verify whether this is correct by doing an analysis on O2. O2 is A, should be equal to 10.02 plus 0.88 divided by 2 plus 5.62 plus B by 2, and indeed this is your 22.20, this is your 12.24. If you do this summation of this individual terms, this turns out to be 22.20, which is means that is you have done it correctly. Okay, so you have now X, which is 1.36. You can write this X in terms of 1.36 C8H18 plus A is your 12.24, okay, plus 10 point, so this gives you 10.02 CO2 okay, so this I can write here, and this will become B is your 12.24 H2O. Now you can convert this thing to 1 kilomole as basis. Okay, for C8H18 this becomes C8H18 plus 16, this is your A, so this should have been your 22.2. Okay, so when you divide this number by this number in order to get the basis for 1 kilomole for octane, this becomes 16.32, okay, which is nothing but O2 plus 3.76 N2, and this is your 7.37 CO2. Okay, so this becomes your basis for with respect to your 1 kilomole basis. Okay. Okay, so what we have done till now is obtain this complete equation for 1 kilomole of octane. So this is a chemical reaction for the combustion of octane, and corresponding to this you have theoretical air as well. Okay, if you look at the problem, the first thing which we wanted to know is air fuel ratio. Okay, so we already know the mass of the air, okay, because with respect to 1 kilomole basis we have already written the equation here. So this is the equation, that means your M air is 16.32 into 4.76 kilomole, because that's a part including the oxygen and nitrogen, and multiplied by the molar mass of air. Fuel is 8 kilomole multiplied for the carbon and then for the hydrogen, so that makes your air fuel ratio as 19.76 kg air divided by per kg fuel. So 19.76 kg air per kg fuel. Now the next question is to find the percentage of theoretical air which we have to use. So now theoretical air is on the basis of the fact that you have complete combustion. Okay, thus you need to write this equation. 1 kilomole of C8H18 plus 8 kilomoles of air leading to 8 CO2 plus 9 H2O plus the inert part. Okay, and from here you can get the theoretical moles of air, which gives you 12.5 by using simply the elemental or the mass balance of air. So this becomes your theoretical air to be used, and thus you can find out the percent of theoretical air, which is nothing but mass of the actual air divided by mass of the theoretical air. And what is the mass of the actual air? Which is nothing but your 16.32 kilomoles. Okay, so 16.32 kilomoles multiplied by, of course, the oxygen plus nitrogen, that means 4.76 kilo. So this is the total kilomoles of air, and this 12.5 theoretical limit, okay, multiply 4.76, and this gives you 131%. So thus in the previous combustion example we used 131% of theoretical air, or in other word 31% excess air we have used in order to have this combustion process for the octane. Okay, so I hope this particular example illustrates how to make use of elemental balances in order to find the theoretical air or excess air or percentage of excess air. Okay, so that will be the end of this particular lecture. In the next lecture we will take up enthalpy balances and other aspect of energy balance related to chemical reactions. Okay, see you in the next lecture.